as we saw that hazards happen when there are glitches. When there are hazards, there are glitches. Glitches meaning that is you have a desired behavior of a monotonic output, but rather you have a, this is an example of a static 0, this is an example of a static 1, and this is an example of a dynamic hazard. And we give an example of a simple logic circuit which is AB prime plus BC, and you have a circuit like this, and because of the unequal delays in each of the path, you can get a static 1. So this is a static 1 hazard. We can get that. Okay, similarly, so now let us identify that why can an static 1 or a static 0 hazard happen. You try to look at the Carnot map, and we have seen that initially let us consider that single input change, SIC mode, which meaning that one of the inputs, so here you have A, B, C, 3 inputs, the value of one of the input will change. Okay, and or rather the value of the one of the input will change. So if you can see that, which means that the transitions of the input from one value to another. So input is a 3-bit number. Say let's suppose it is 0, 0, 0, and then it changes to 0, 0, 1. So this is a single input change. So if there is a single input change, you can see the transitions, if you plot it over the Carnot map, is over adjacent cells, because you know the adjacent cells of a Carnot map differ by only 1. So they change by adjacent cells, change over adjacent cells. Now let us look at the sum of product form of a function. So this is a sum of product form like AB prime plus BC. This is a sum of product form. So if you are talking of a static 1 hazard, the f should be statically 1. When is f statically 1? F is desiredly statically 1 when, so this is a sum of product. So at least any one of these product terms, so either AB prime or BC, is 1 all the time. So the output f will be statically 1 since it is OR. If at least one of them, any one of them is 1 throughout the transition. Okay. So you know what are each of these terms? Each of these terms are nothing but one min term. These are nothing but min terms. So every term in the sum of product would correspond to a min term or a cube. If not a single min term, a whole cube. Okay, like AB prime is this cube. AB prime is this cube, whereas BC is this cube. So they are cube. So now if we have a transition, say from one of the min term to another, let's say from this top one to this one, let's say there is a transition. That means before the transition, one of the cube is 1, and after the transition, another cube is 1.
Hello.
Hello. Yeah, please. You want to say something? Hello. Am I audible?
Yes, sir, you're audible.
Okay. All right. So we are doing a transition over adjacent cells of the Carnot map, and if two adjacent, and this is a static 1 hazard, so we are transitioning between a one cell to another one cell. It's if it is a dynamic, it would, because for the output f will be 1 only when any one term in the one min term in this Carnot map, that is any min term marked 1, that is on. Okay, for example, if say A, B prime, C prime, so then the input pattern is 1, 0, 0, then this term is 1. So if you are talking of a static 1 hazard, definitely the transition should have been from one cell, any of the cell marked 1 to another cell marked 1. Let's say this transition happens. Okay, and why is hazard happening? Hazard happening because, see, if at every time at any one of these product term is 1, then it's fine. any of the product term 1 means if it is part of any of these cubes, then it is fine. So what is happening during transition is, let's say we are moving from one cube to another cube. We are moving from one cube to another cube. Okay, in between, that's why this glitch is happening. Maybe in between we have because of the glitch we have moved, because of the delay we have moved to something else. That's why this happened. Okay, so this thing you try to realize, as long as you are moving inside the same cube, there is no glitch. Only when you are transitioning from one cube, let's say this cube, to another cube, there may be a glitch in between. And of course, in order to be a static one glitch, you have to move from a one cell, a on cell to another on cell. So it is very easy to detect whether this type of hazard is there or not. Okay, so how to detect? You look at all possible one-to-one transitions. Look at all possible. So this is a one-to-one transition. This is a one-to-one transition. This is a one-to-one transition. And you see that both the startup transition and end of transition, both cells, they are covered by the same cube or not. If they are covered by the same cube, that will not lead to a glitch. If you are not covered by the same cube, that means not covered by the same cube means what? Before the transition, let's say AB prime was 1. And after the transition, AB prime becomes 0, BC prime becomes 1. This will cause a glitch. But if throughout the transition AB prime stays AB prime, both it stays 1, then there is no glitch. So we'll look at transitions from which are from one to another one cell, which are in different cubes. So naturally, this is a problematic transition. This may lead to an hazard. This transition, whereas this transition is not a problem, this transition is not a problem, whereas this transition might be a problem. So all you need to do is to, given a Carnot map, you have to look at possible one-to-one transitions which are part of different cubes, and each of them are a potential hazard. Each of them may lead to an hazard. Okay, so what is the solution? The solution is you have another cube, an additional redundant cube, which covers these transitions. We call that as a required cube. We have another required cube which covers these transitions. So what is the cube that will cover this one transition? Can anybody tell? What will be the cube that covers this one transition? Please tell. What is the product term for that? Just think and tell. We are transitioning, say, 0, 1 to 1, 1, and A is 1. So the transition will be AC. So what we do, we add another term AC. So let us see what we do. So we'll try to cover this. We'll try to cover this with another additional cube which is redundant. So we add this term AC. So now all the possible transitions from 1 to 1 are covered by a single cube. Okay, so this transition is covered by this cube, this transition is covered by this cube, this is by this. So we add this additional term. So what does that mean in the circuit? Means we have another AND gate and we have a 3-input OR gate. Now see, whatever transition you take, whatever transition you get, at least one of these product terms will be 1. Okay, that means the F will always stay 1. It will never have a glitch. It will always stay 1. Okay, so by adding this additional redundant cube or an AND gate, we can cover this hazard. We can cover this glitch. It will not happen. Okay, so all you need to do again is that, suppose this is a small circuit. If you are given a bigger circuit, you need to look at what are the required cubes and add redundant gates corresponding to the required cubes, and that will make it hazard free. It's very simple. But all this works for single input change. That means you are transitioning only between adjacent cells in the Carnot map. Okay, single input change. Now, what happens if there is a multi-input change? Multi-input change means you have a kind of a path. It's not that only one input changes from. So here the only change is that you are changing from 101 to 111. That's this transition, 101 to 111, only one input. But in general, we can have multiple of these inputs changing. For example, if you look at these arrows, if you look at these arrows, these are actually a multi-input change. So this solid arrow, for example, the input changes from 1010 to 1111. Multiple inputs have changed. Similarly, here also multiple inputs have changed. Okay. So what we do is that basically you split it into a number of SiC transitions. You consider this. Okay, by the way, I have drawn two type of arrow. We'll see that one type of arrow, note that all these are static one transitions. You are transitioning from one cell to another one cell. So it's not dynamic. You are still doing a static one transition. Can anybody tell that what is the difference between this dotted arrow transition and the solid arrow transition? What is the difference? So one of this problem is due to the circuit that you are using, which is the logic hazard. It's due to the circuit that you are using. The other one happens, it is inherent, it's a function hazard, it is implicit to the function that you are using. Okay, so that is implicit. Okay, so how do you detect and remove these MIC hazards? What you do, you split. So for example, look at this solid arrow. We are doing a transition from this input to this input. So I break up it into a number of SiC transitions. So so this is a combination of how many? 1, 2, 3, 4 SiC transitions. So one here, another here, one possibility, another here, and then here, another possibility. Okay, and then you try to look at each of these SiC and try to remove them. So you'll basically need more number of redundancies to remove that. Okay. Basically the same philosophy. You try to cover it with an additional cube and have that redundant gate and try to cover it. Okay, so this is the thing. But one thing, let me tell you. So we are talking about this. So this is a synthesis technique where if we make it too optimal or too minimal a circuit, because of these delays, you may get this hazard. So you have to sacrifice some minimality and have some of these redundant gates to cover up for the hazards. But these problems really happen when your input asynchronously changes. It can change anytime when it asynchronously changes, and that's why there is output. And you immediately want to see the output. So there's an immediate input change, maybe just a little bit of time after that. So that is the root of the problem. That's where hazards or glitches will create problems. So an alternate approach is that you wait for some time. You wait till it stabilizes. After that, you look at the output. You consider the output. Okay. So so this is naturally. So how do you decide after how long will wait for the achievement? You use a clock, and you use a clock width which is more than the time of the glitches. Glitches are very momentary. It's around the time of the delay of a circuit, which is very, very less. Okay, so you have a clock cycle which is wider than these delays. And you wait for a clock cycle and the glitch will settle down by that. After that, you consider the output. So since you are using a clock, naturally, this is a synchronous system. So if you are using a synchronous system, then glitches create less of a problem. except for things like millimachine where you have to immediately look at the output on input, except for that. But so the modern way of handling hazards is by using a synchronous circuit. In asynchronous, you can still get hazards, and you have to have this kind of redundant designs. Okay, I am not going detailed of MIC hazards. These are a little more involved, but the basic idea is the same. You extend the, you cover up, you have redundant gates, and maybe in the notes you have them. If time permits, we'll look into that later. Okay, so I'll stop here now. I'll stop here now, and I will go to the test.